Just FYI, I'm still on the US time zone, so I'm like already sleepy. It's past my bedtime, and I have a slight cough. If I do cough, I apologize. All right, let's start. So, Jean Dubry, Krakow. My name is Sandeep, and I'm a functional programmer. And today I'm going to talk about Tagless-Final, Cat's effect, and LSM trees. In the past, a lot of NoSQL systems have been based on the idea of LSM trees. I wanted to learn more about LSM trees, so I decided to read up the material. I read a few papers, and I decided I want to build one. So if you look at the systems like Cassandra, RocksDB, LevelsDB, they're all based on LSM trees. One of my other interests is functional programming, and so when I was looking to build this project, I looked around, and Cat's effect was available as a functional programming library, so I picked that up. Disclaimer, I'm not an expert. If I make a mistake, feel free to correct me during the Q&A, or meet me after the presentation and we can talk more. I have the link for all the sources that I've used in my slides at the end. So LSM, how many people are familiar with log structure merge trees here, by the way? Okay. So you can think of LSM trees as an index that accumulates writes in memory and then writes them on disk using sequential I/O and merges them using sequential I/O. So the red here represents a traditional index, and the blue here is an LSM index. So the traditional indexes do in-place mutation. They are, so you could think of a B+ tree as a good example. They are read optimized. Writes cause random I/O. Writes and updates can cause page fragmentation. On the blue, on the other hand, the LSM index, they never overwrite existing values. You're effectively always appending a new value. So here in the traditional index, if you look at the key K1, V1, if you want to update that tuple with a new value, K key 1, V3, you go find that value in the index, and you override the existing value. In the LSM index, you just create a new entry, and you're done. So this is where the notion of log comes in. Effectively, you're adding a new value to your index. So this is the original LSM design. The original LSM design had multiple components, C0, C1, C2, CK. C0 component lives in memory, C1, C2, CK, etc. actually are on disk. They're all B+ trees. C0 incurs the writes since it's in memory. Say any component, say CI, is full. A leveling merge or a rolling merge process will be triggered that collects the leaf pages from the component, and then merges them, starts to merge them, and adds them to the next component, CI plus 1. So one of the issues or complexity with the design is that if you're trying to read from a leaf page that is being updated by another process, you're effectively blocked, and there's no way around it. So this is the current design of LSM trees. It introduced the concepts of levels and components. Each level, L, has T components. It improved on the original design by making the disk components immutable. So here, level 0 is in memory. It's usually implemented as a skip list or a B+ tree. And the disk components here are on level 1 and level 2. These components are usually the disk components are usually also known as SS tables. This is if you have read any literature on Cassandra, this is where the name comes from. It's sorted string tables. The disk components contain, or the SS tables rather, contain data keys and index. So the data block actually has the key value pairs ordered by keys, and the index has just ordered keys. So here I'm actually just showing a level 1 and level 2, but effectively you could have multiple levels, and you can have multiple components, and this is all configured by settings, external settings. So let's look at the read path in an LSM index. Say you're trying to look for key K1 or key K, and it's not present in level 0, so that effectively it's not present in memory. So you're going to go and read the disk components. So Say there are L levels and there are Tn components on each level, and say the key was present on Lth level on the Tnth component. So then you'll effectively end up scanning all the components. Say a new query for key K prime comes in, and it's not present in the index. You will still go through the exercise of scanning all the disk components, and this is bad. Like the performance actually degrades as you collect or accumulate more components. So there are a few optimizations that you could do, and let's take a look at a few of them. So how many people know about Bloom filters? Nice, okay. So Bloom filters are effectively probability-based data structures. They answer simple questions about set membership. They have two operations on them, insert and check membership. So the figure here actually shows the internals of a Bloom filter. You can think of it as a bit array, and then of size m, of some size m. So for insert operation, we take the key, we hash the key, we generate the addresses into the Bloom filter. You go to those addresses and you flip those bits to 1. For check membership, when you get the key, you do the same. You take the key, you apply the hash, you get the addresses. You go to those indexes and you check the index values. If all the index values are 1, you say that the key is present. And if they're not, you say the key is absent. So Bloom filters, there's a chance. So Bloom filters can have false positives, but not false negatives. What does that mean? If the Bloom filter says that the key is not present, you can be sure that it's not present. But if it says that the key if it says the key is absent, then you could be sure that it's absent. If it says that key is present, that there's a formula associated with it that you could use to calculate the probability of the key being there. So in this formula, if the n is the number of items in the filter, m is the size of the filter or the bits in the filter, and k is the number of hashes or the hash constant. So let's look at an example of calculating the false positive. Say you have 1 million keys, and you have the size of the Bloom filter is, say, it has 17 million bits or closer to MB, and the hash constant here is, say, 5. Then 1 in every 1,000 requests will actually go and search the block, or that's the probability of false positive. So a Bloom filter actually exists along with all the SS tables. So before you actually consult the disk components, you actually consult the Bloom filter, and if it says, okay, yeah, the key is present, then you go on and scan the disk components. Otherwise, you can skip it. Another optimization is called partition tiered merging. So each level actually has key ranges except for level 0. And this is good because it helps with performance, write performance bursts. Level 1, and when you're trying to merge SS tables from any level into the next level, L+1, you select the SS tables with overlapping key ranges, and then you merge them to form new SS tables on the next level. So here we are effectively collecting the SS tables marked in red on level 1 and level 2, and then forming new SS tables represented in orange at level 2. So what we are doing here effectively is taking the key range and then partitioning them and then merging them next on the next tier or level. That's where the name actually effectively comes from. I'm not showing level 0, or there could be more than 2 levels here. But in the figure here, each rectangle represents a group. In horizontal partition tiered merging, the SS tables in a group are selected, and then you form new SS tables on the next level. So what you see here, what you see here is the SS tables from one group can be added to multiple groups on the second level. This is called vertical grouping. So the key insight here is that the key ranges are disjoint. You have 031, 030, and then there is 012 and 1731. What this means is that the size of the SS table is not fixed because you're dependent on the key ranges. The issue with this design is now if you want to understand the performance here, you need to have extra bookkeeping. If you think about it, say you have a hot range, that is going to dominate your performance in terms of like I/O and whatnot. So it's always good to have fixed layout when you're trying to like do anything related to performance. Again, I'm skipping adding level 0. There could be multiple levels. So in this case, each rectangle at a level represents a group again. In horizontal tiered partition merging, each level has an active group that receives the SS table. Here we select the SS tables from both the groups at a level, and then we could add it to a new active group on the next level. So here we are collecting the SS tables from level 1 from both the groups, and then adding it to an active group on each level. So in this scheme, you have an active group that receives the SS table. On the other hand, on this one, there is no notion of that. It's just disjoint key ranges. So one thing about this, the key idea in this design is that the SS table size is fixed. Yeah. All right, so this is the SS table designed for ArKi key value store. It has a data byte buffer, index, Bloom filter, and footer. So data byte buffer contains the data that's page aligned. The page size on most architectures is 4K. And so you can think of page as a basic unit of data transfer from main memory to an external device. In this case, it's a disk. So this is also called paging or swapping if you're going back and forth in the data. Index it stores the keys. It also stores the page number and the data offset for the data in the data byte buffer for a key. So it's a tuple, key, page number, and the page offset. And you'll see why we need those things. Bloom filter, we've already looked at it. There's nothing interesting here. Footer is just min, max, and the offsets for all the data structures up here. All right, so let's go through some code. So I'm not going to go into too much details about what's happening, but I want to highlight some interesting bits in the code. So we'll first go through the write path or the put path. So this is the interface for ArKi key value store. Let's look at the implementation of put. So put here is internally calling put 0 and process frozen memory block. That calls actually add 0. Let's look at the implementation for add 0. So this is the partial implementation for add 0. You see that we are actually maintaining a lot of state when we're trying to add data. So all this stuff in the red, I don't know if you guys could see that, but the stuff in the red is all the internal state that we have, max allowed bytes, current page offset, and CMAP, which is actually a concurrent map list. So we first check to make sure that the data, when we're adding the data, it's within the, it's less than the max allowed block size. The default is 64 MB, and this can be configured through a setting external to the application. Next, we make sure that the data is page aligned. We don't want to exceed 4K. We do that check. And then if everything is good, we go ahead and add it to the CMAP. This is where you're effectively adding the data at level 0. This is the in-memory component of your LSM index. All right, so let's go back to our put method. So once the add 0 returns, it actually, if the block, the in-memory block is actually full, it will return a frozen in-memory block. That's what's highlighted here. So this frozen in-memory block now needs to be processed, turned into an SS table, and then written to disk. So the processing happens in the process frozen memory block. Let's look at that code. So this is the implementation for process memory block. I've highlighted writer. That has two methods on it, build and write, that's used to do all the processing. Let's look at the implementation of these two. Again, the build method has a lot of internal state, some of it which we have already seen in the design slides. So you can see the index there, you can see the page aligned data buffer there, Bloom filter, all that stuff, not that interesting. So let's look at the put on the Bloom filter. So this is the implementation for put. But there's an interesting bit here called GetBit. Let's look at its implementation. So the implementation for GetBit actually takes 2 hashes and a counter. And this counter is the K hash counter from the Bloom filter slides that we saw earlier. So this is the number of hashes that you need for your Bloom filter. So so generating a good hash is CPU intensive. So the literature suggests that you build out a 128-bit hash. Say you have a in-memory block containing 1 million keys, and the hash counter, or the number of hashes, k is equal to 5. Then for each entry, you're going to generate 128 k, or in this case is 5 128-bit hashes, which is actually a performance bottleneck. So using this method, you could actually generate the hashes or the addresses into the Bloom filter in a performant way. So this technique actually, what it does is it takes 2 64-bit hashes and the hash counter, and then using this expression here, you could actually get pretty good entropy and distribution in your hashes. There's actually a link that talks more about this design or this trick I've added to the slides. If you're interested, feel free to check out. So let's look at the process frozen block method again. So we've already seen how we build the Bloom, the SS tables. Let's look at how we write to disk. So this is the partial implementation of the write method. Here I've highlighted the resource type, and this is it's pretty interesting. If you have used try catch finally on the JVM, this is basically try catch finally on steroids. Let's look at its usage. So makefile here actually takes a random access file and creates a resource out of it, which will close automatically. So if you look at the highlighted code here, this is how you use the resource. There's a use method on it that yields the underlying resource. And then you could use the resource in the scope of the use method. And it'll automatically be deallocated after, or garbage collected, or closed after the scope is closed. If you look at this, then this is not that different from try catch finally. But if you look closely to the signature of use, then you will see that use can actually run any arbitrary effects in F. And F here is an I/O computation, and it could be any I/O monad. And then you could think of any I/O computation, and there are multiple types. One could be like concurrent or async, or they could be parallel. Try doing this on the JVM in try catch block. Try to run an asynchronous computation on a try catch block, and it's not fun. Actually, it doesn't work, but it does work, but it's not fun. The result is unpredictable. So a better way to think of a resource is you should think of resource as a region in which you have your resource that you could use, and once that resource goes out of that region or that scope, it'll be garbage collected for you or deallocated for you. Another way to think about a resource type is a way to run pre-pros conditions for your resource while it's being used in the region. So this is, once you have the channel, you could create, once you have the file, you create a channel of it. After you creating the channel, you write data, and then you could write the index. Once you're done with the index, you write the Bloom filter and the footer, and you're done. So the T in the, so we're back to the process frozen memory block method. So the T in the T.start method is actually a concurrent effect type. The concurrent effect type actually helps you run I/O computations concurrently. The T.start takes an I/O computation that yields a fiber. And you could call join on the fiber, and the fiber will resume its computation once the I/O computation within the fiber has completed. So the API here for the fibers is very similar to JVM threads. You can see start and join. So I hope everybody knows what late binding is. So the type constructor F here will be bound to an implementation of IO monad. In Scala ecosystem, currently there are 3, Cat's effect, Monix, and ZIO. So effectively, all these IO monads implement green threads on the JVM. A quick primer on JVM threads. The JVM threads and the OS threads are one-on-one. That is, they are the same. But using the IO monad, you could run multiple IO computations on the same thread. And this is possible because they are implemented using cooperative scheduling, and then they will yield back to the control loop after a certain op count or an operation count. And this is actually good if it's trying to schedule your payload with fairness. It has some caveats, but for general fairness payloads, this is a good way to think about the design of fibers or IO monads. All right, so let's look at so that was the write method inside the LSM index. Let's look at the get path or the read. So this is the implementation for get. The unhighlighted part is just if the key is present in the memory, you just look it up and you'd return. The interesting bit is when the key is not present and you're going to the disk. So when the key is not present, you first try to search the Bloom filter. And if the Bloom filter says, OK, the key is there, you go ahead and then you search the index. This is going to be a binary search, straight up binary search. If the key is present in the index as well, it's going to return a tuple of the key, page number, and the page and the data offset of the data in the data byte buffer. And so once we get the search result, the tuple, you could calculate the page offset inside the data byte buffer now, and you could finally return the result. The address calculation is as simple as taking the page size, multiplying it with the page number, and then adding the offset, and then jumping to it, and then return the data in the data byte buffer offset. All right. So IO on JVM. So the LSM index, the way LSM index gets its performance is through sequential IO. And on the JVM, there are a few ways to do IO. So one is memory map. So if you can think of memory map as a way to map a region of the file in the kernel memory and use it and access it as if it was part of the user space. Effectively, data is cached and it's page aligned. So map byte buffer is a way to memory map regions on the JVM. It's a direct byte buffer. So the way to so the direct byte buffers. Do people know what direct byte buffers are? Anybody? Okay. So direct byte buffers are natively allocated memory with a pointer on heap. Okay. So all right. So let's look at unsafe API. How many people know what unsafe API is on the JVM? Okay. So unsafe API is another way to do I/O, and a lot of frameworks actually use it. When I started designing this, I actually used unsafe API, but I moved away from it because it is not going to be supported by future versions of JDK. So when I say a lot of frameworks actually use it, a lot of frameworks like Netty, Spark, JNR, JFFI actually all internally use it. So some of the issues that I faced with memory map on JVM. First is page alignment. Up until JDK 6, everything was page aligned. So if you allocate a direct buffer, you will actually get a page aligned 4K direct byte buffer. But post JDK 6, from JDK 7, all the byte buffers are 8 byte aligned, sorry. That'll be bad, right? Okay, so direct byte buffers, cleanup. So there is actually no unmapped method to reclaim the direct byte buffer that you've just allocated. There is the Sun Miscellaneous Cleaner API, but then the deallocation semantics are not deterministic. Another issue is, but so there's a way to clean these direct byte buffers. This is where JNR JFFI comes in. And they actually expose a lot of other things, but you can use those to actually clean up the byte buffers. So a Project Panama could actually help with this a lot. Has anybody heard of Project Panama on the JVM? Okay. So limited memory map handles, if you don't have any serious project, if you don't have enough memory map handles, the JVM will crash. There's no way coming back from it. 32-bit signed integer addressing. So the direct byte buffers use 32-bit signed integer for memory map, for addressing memory maps. So effectively, you could only ever create a 2 GB memory map region at one time. For large files, you have to create multiple memory maps. This is an issue, say that you try to access a memory map that is reclaimed, then that's a JVM crash. There's no coming back. You've lost all your state. These things are very hard to debug. If you have not seen one, good for you. I hope you don't see one. And you've lost all state, and then So imagine that you have a set of you're trying to do I/O on a really big file, and you have a set of memory map regions, and now you have different threads trying to access it, and you're trying to deallocate this for whatever reason. So now what you have to do is you'll have to synchronize your access to these memory map regions, but then that kills performance. And if you don't do that, then there's a very good chance that you could actually crash your JVM, because it might access a memory map region that's actually deallocated. So issues with LSM trees, write space amplification, SSD lifespans. So when you write data to an LSM index, it might actually trigger a compaction process. It might incur more I/O than what you expected. So say you have like 500 million key value pairs, 16-byte key and value is say 128 bytes. So effectively your user data is 45 GB. So on level DB, there's 27x amplification. I'm sorry, excuse me. That is close. You're writing close to 1,222 GB, and on RocksDB that's 42x amplification, and you're effectively writing 1868 GB of data. Write amplification also affects throughput, and it actually decreases the lifespan of SSDs. Writes can also stall during merge process if you're trying to merge these SS components, these SS table components. So tuning, so the RUM conjecture states that no access method can be read, write, and space optimal. LSM trees actually provide with a lot of knobs, memory, configs, Bloom filter sizes, like partition policies, etc. So tuning them is tricky. Like you have to measure, and you have to be very cognizant about like what you're measuring. Secondary indexes. So LSM trees provide a very simple key value interface for non-key attributes. You need secondary indexes, which the LSM trees don't provide. So some of the improvements that are happening with LSM trees, one is non-volatile express memory. They have better random I/O and better better lifespan than SSDs. Whiskey, this is another paper from Wisconsin University. The key idea here is that you separate the keys from the values. The values will be straight up log, and the keys are actually added to an LSM index. Since the size of the keys is small, the data you're writing is small, so the I/O will be less, and it'll be more performant. So this is actually used in a graph database called Badger. It's written in Golang. PebblesDB, this is also interesting. It's also called like FLSM trees or fragmented LSM trees. So they borrow the ideas from concurrent skip list. They introduce the concept of guards that help you segment the key space. So segment the key space into disjoint key ranges. Once you introduce a guard, it's actually going to be present in subsequent levels. All right, so Tagless-Final. How many people actually know what Tagless-Final is in Scala? And okay, a lot more hands went up. That's good. All right. So all the content here is from Oleg Kislyav's paper or course on Tagless-Final. I have the link at the end, or you could Google it. I hope everybody has heard of Tagless-Final in Scala. So it's deemed as an alternative to monad transfers and monad transformers and free monads. Monad transformers and free monads are very big topics on themselves. I'm just going to give a very, very simple and naive definition for them. So for monad transformers, you can think of monad transformers as a stack layer of monads that help you run the computation using the underlying monad. And for free monads help you encode your stateful computations into an algebra that then you run via an interpreter. The key insight here is that you could build any monad for a functor f. So let's understand, when I was trying to understand Tagless-Final, whenever I read about it, I did not know the meaning of what Tagless and Final meant and where did they come from. In the end, I understood that it comes from Haskell. So let's try to at least understand what these mean, even if we never have to use them, like the actual words, I mean, or the definitions. All right, so types and tags, I'm pretty sure everybody knows what types are. Types help you statically prove the absence of certain behavior. Tags are runtime labels that help with runtime representation. So let's look at some Haskell. So let's look at a very simple algebraic data type here. This algebraic data type expression has defines a very simple language that has literals, negation, and addition. If you encode the expressions of a language as the values of an algebraic data type, that's called an initial embedding in Haskell. As a side note, when you embed one language in another language, that's called a DSL, domain-specific language, or EDSL, embedded domain-specific language. So let's look at the interpreter. The interpreter runs the expression, that's the expression that we're talking about, runs the expression using pattern matching. So we could embed the language a little differently. We could actually introduce a representation type here called rep_r equal to int. Once we do that, now the language, the three expressions, so the three expressions now form a language in the domain of rep_r, or put in another way, the language has denotational semantics over the domain of rep_r now. Denotation semantics is an approach for formalizing and the meanings of languages by building mathematical objects called denotations. And these denotations actually represent the expressions of the language. If you read the paper, it further explains or goes into and talks about the type classes, interpreters, evaluators, the expression problem, and how the type classes solve the expression problem. Then it actually goes and talks about the initial and the final embedding using generalized ADTs, and also the higher order abstract syntax type. So that's what the final and the final tagless comes from the final embedding. At least you get some sense of what we're trying to achieve if you see something like this. Okay, so let's come back to Scala. So this is an API or a module for range. So in the first example, how many people actually use Scala? Okay, good. So this should be pretty vanilla for you guys, right? Okay, so the first example, we have the API is actually tied to future. Say if we wanted to make it a little bit better and make it generic. We say in the effects world, we say that, okay, the effect type there is the future effect type. So one way to do this is we parameterize the ranged module with the type constructor f, and now our return types are generic. But by doing this, we've actually, now F is too strong, or actually it's unconstrained, and now this algebra is actually too, there's no, you don't have local reasoning in this. It's basically too powerful, you could do whatever. So let's take an example of this generic data access layer. So we have this type constructor F here. It takes along and returns an F of A, but it doesn't tell us what exactly this function does. It could do anything, and it depends on that F. But F here is unconstrained again. Looking at just this signature, you cannot tell me what this does. So now we have constrained F by the monad effect type. So the monad effect type effectively gives it the capability of sequencing the expressions or threading through state. So now we could like reason more, okay, I could at least expect something of that nature to happen here. Now we have further constrained our F type constructor with context shift. By the way, context shift, those who are not aware, it deals with moving computations back and forth between thread pools. And you could do a little bit more than that, but yeah, so by adding the context shift effect type here, it gives it the capabilities of thread pool management. Further constraining F to monad error, now we know that this function can also handle monad error. I mean, there's error handling present here. By pushing more type information into our APIs and algebras, we could actually have more reasoning without going into too much details of the implementation. You have more local reasoning, and that's what you're looking for by just looking at the APIs or the signatures. So constraints liberate and liberties constrain is actually a very good talk. If you guys haven't looked at it, just check it out by Runar. So here a range algebra or API, whatever you want to call it, is actually constrained by sync, async, and concurrent context shift effects. And these effects actually are, they have laws and properties with which you could reason about them. And so these, once you have effects that are backed by properties and laws, you have small building blocks to actually produce much more complex functionality that actually has more local reasoning than anything that you've done, like anything that you see on the JVM. Okay, so next is bring your own effects, BYOE. So this is, as a library author, you could actually introduce, or you could try out new effects in your localized module without having to worry about changing the APIs or breaking your consumer. You could actually implement new new implementation for your algebra by just implementing those constraints. So, okay. Lessons learned, byte buffer is terrible. Has anybody ever used byte buffer, by the way? Okay. They are terrible. They are painfully mutable. They have this notion of, they track state with 3 pointers, capacity, limit, and position. And for any time you need to read or write, you need to flip the byte buffer and then read or write. But then it's just very confusing because say that you have a common byte buffer and you want 2 threads to access the same byte buffer. Now you need to somehow coordinate these 2 threads to understand what's happening and which mode you're in. And it's madness. If you've never dealt with it, I would suggest you'd rather use Netty. So Netty has its own byte buffer called bytebuff. It has like read and write counters, and they are independent of each other, and you can move around inside the byte buffer without actually worrying about losing data. Another one is, or another trick that you could do is have an immutable view over the byte buffer that has its own state and does not touch the byte buffer. That's what Scodec, does anybody know about Scodec on Scala? I've heard of it. Yeah, that's what Scodec actually does. These 2 are really good options if you ever have to deal with bytes. Go check them out. Another issue is new paradigm and domain. This was interesting. So before this project, I had never worked with effects. So when you're trying to express a business problem using this idea or this library, you have to somehow understand the capabilities or the laws behind each of these effect types. So expressing this is you have to like think a lot, think about the algebra, and then try to come up with the design, which is, it takes time. Yeah, so my recommendation here would be just go and look at the laws or the tests that these libraries have and try to understand what they mean, or at least try to understand what they're trying to do. Just try to break something, just change the variable, make the test fail, and see what they are doing. Effect hierarchy, so here if you see, okay. So if you see that concurrent is actually the child of async and sync, that means whenever you want to use the concurrent type, you need to have an instance of async and sync present in your module. And sync, on the other hand, is almighty God. It's capable of doing everything. And once you say that concurrent is sync, that means concurrent is also able to do everything. This means that you again lose the local reasoning, what we were trying to achieve in the first place with this design. So this is, yeah, it's a design issue. And I think that they are trying to improve this in CATSFX3 design. So debugging, it's like, for this project, I use Printline. There is no good tool to help you with debugging. I'll be very honest. Like, I wish there was a tool which, you turn on a mode that's not in production mode, and you could get like internal state of your computations. Yeah, that's all that I could say about that. But yeah, debugging right now is like your Printline. So general design issues, there are like few. So this is, I say this is the curse of the first. So CATSFX was effectively the first IO effect type library on the JVM. And once it was released, there's a lot of consumers, so there's like, they have to be very cognizant of not breaking their APIs. There are a few issues that actually are present in the current implementation. One is effect locking. So say that we looked at context shift. Excuse me. Say that you have an IO computation and you send it to a thread pool. It runs, but then during the IO computation run, if it meets its first async boundary, and if you don't understand this, feel free to talk to me afterwards. If it meets its first async boundary, it'll actually come back to the original thread pool from where the computation was pushed off from. So that's actually counterintuitive when you're actually building the system. Another one is interruption. Yeah, this one is also tricky. So there is a way to make all your IO computations uncancelable, but sometimes you need the ability to do cancel or interrupt so that you could reclaim your resources from the system. So that's it from me. Thank you everyone for coming, listening to this talk. If anybody has questions, feel free to ask.